Have you ever marveled at how complex machinery, like a robot, can be controlled with what seems like remarkable ease? It often comes down to the unsung hero of human-machine interaction, the graphical user interface. Robot graphical user interfaces, or GUIs, are meticulously designed using user-centric principles, always prioritizing simplicity, safety, and efficiency. They are not merely pretty screens, but carefully crafted tools that enable seamless human-robot collaboration. At their core, robot GUIs are fundamentally different from general-purpose computer interfaces because they must directly address the unique physical and operational characteristics of a robot. The design process begins with a deep understanding of the robot's specific task, whether it is precise surgical manipulation, heavy industrial lifting, or autonomous exploration. This task specificity dictates everything, from the layout of controls to the type of feedback provided. A crucial aspect is enabling robust feedback and feed-forward mechanisms. The GUI must clearly visualize the robot's current state, its precise position, orientation, and even the forces it is experiencing. Equally important is feed-forward, allowing the operator to preview plan movements or understand the consequences of their commands before execution. This builds trust and prevents costly errors. Furthermore, designers carefully consider the level of abstraction required. Some users might need low-level control over individual joints, while others requiring high-level task-based programming where they simply instruct the robot to pick and place an object. Balancing these needs is key to minimizing cognitive load and ensuring the interface is intuitive for its intended user, reducing the mental effort required to operate the robot. To translate these principles into a working interface, designers follow a structured process. It starts with rigorous requirement gathering, interviewing potential users and observing them interacting with existing systems or even mock-ups. This helps pinpoint specific needs, pain points, and workflows. Then comes iterative prototyping and testing, which involves creating wireframes, interactive mock-ups, and even full-scale simulations. These prototypes are tested with real users, and their feedback is invaluable for refining the design. Selecting the appropriate interaction metaphor is also critical. Should it be direct manipulation, where users drag and drop objects on a virtual representation of the workspace, or a more command line-driven approach for expert programmers? Environmental factors, such as the use of touchscreens in dusty industrial settings or specialized haptic devices for remote control, also heavily influence the design choices. A fascinating detail in GUI design for robots is the application of established human-computer interaction laws, such as Fitts law, which predicts the time required to rapidly move to a target area. This helps optimize button sizes and placement for efficiency and precision. Many robot GUIs also heavily leverage advanced simulation environments, often built using tools like RViz from the Robot Operating System, or ROS. These simulations allow for extensive testing of GUI functionality and robot behavior in a virtual space, validating the interface before deployment in the physical world. This ensures that the interface provides clear affordances, meaning its design inherently suggests its function, making it easier for users to instinctively understand how to interact with the robot. Ultimately, the sophisticated design of robot GUIs serves to bridge the gap between human intent and machine action. By carefully considering the user, the task, and the robot's capabilities, designers create interfaces that transform complex robotic systems into powerful, accessible tools. This ensures that robots can be operated safely, efficiently, and effectively, unlocking their full potential to assist and augment human endeavors.
If you love robotics, like, subscribe, and keep building with us.